solving systems algebraically using substitution or elimination. And I asked you guys to work on 9 through 18 from the problems. So we'll start with some questions here. For starters, does anybody have anything, Grace? 16? Sure. You should have gotten no solution. That's correct. Oh, okay. No, so you can tell, one way you can tell just from looking at this. We notice that the variables are like one equation is 2 times the other, but the constants part at the end is not 2 times the other. So I can tell just by looking at this it's going to be no solution. So that's excellent that you got the right answer. Leo?
And the only time it's all solutions is just when it equals each other, right?
Yeah, if they are like, one is just like a linear combination of the other, just like everything is times 2 or times 3 or whatever. You know what I mean? So that's good. And again, if you had done that, I don't even think you needed to do the substitution. If you had noticed that right from the get-go and just said, hey, I know it's no solution because of this. Now, if you do the substitution, that's fine. I wouldn't expect most of us to notice that right away. But if you did notice that, you could certainly use that as a justification for your answer and not go through any of the algebra. Okay. Joe?
What does it mean when it's like times 2 and then times 2 at the end?
That would be infinitely many solutions. Yeah.
Solutions? Okay.
If they were all the same factor.
Okay.
Yep. If the variables are the same factor and the constant's a different factor, that's no solution. And if they're, like anything else is just 1. Joe?
Could you do number 11, please?
Sure. So 11 again asks for substitution, I guess. So 6x minus 2y equals 5. And then negative 3x plus y equals 7. So first thing I'm going to do is pick an equation and a variable to get by itself. I would pick the y from equation 2 because I don't have to divide anything, so there won't be any fractions rattling around for me. And if I can avoid those fractions, that's usually helpful. Again, not that you couldn't do it with the fractions rattling around, but like, why would you want to if you didn't have to? So what I'm going to do now that I got the y by itself is I'm going to take this y that I solved for and substitute it into the first equation. So 6x minus 2, and then in place of y, I'm going to write 3x plus 7. So when I do that, I can distribute the negative 2 through. And I notice that that stuff all drops off, and I have no solution here, right? Since I have things that are not equal. You could have also noticed that this is like negative 2, this is negative 2, and this would be like 7/5. Certainly not negative 2. Which again, if you had noticed that right from the jump, you could have said no solution there. I went ahead and did this one because I wasn't paying attention. I didn't notice it right away, but as soon as I saw what was happening, I'm like, oops, guess I could have done that the shorter way. Oh well. You know what I'm saying, Joe?
Yeah, so to start problems like this, you just look to see which variable or like which equation you want to.
Yeah, and it doesn't, and to be technical, it doesn't matter which one you choose.
Yeah. It's easier to do like this.
But like if you can avoid having some fractions, I typically would want to do that. But it's not the end of the world. In some problems, it's unavoidable to get fractions with.
So then you do that, you plug it in, and it's basically kind of just algebra.
Yeah, and that would get you your first solution. Then you plug that back anywhere
Yeah.
where you have two variables, and you
Okay.
can get the other.
Okay, sounds
Anybody else? Again, this was all, very much things that we had done last year. Nothing really new and more complex, so that's nice. So let's finish up here talking about section 4. And when we're done with that, we'll do the homework quiz that you guys probably all knew were coming. Mostly, we're going to do it at the end just so that, in hope that the few people that are still absent maybe show up and are able to do things. What's up, bud?
So which parts are going to be on the homework quiz, like your sections?
Well, at this point, we would have talked about the first 3 sections, so obviously what we're doing right now would not be on the homework quiz.
Yeah.
So when we talk about solving equations in 3 variables, there is not a graphical method that we'd use for this because we don't really have the tools that can graph things in 3 dimensions, like our calculator can't handle that kind of a problem. So we're really stuck with just doing substitution and elimination. But that's okay. They're basically still the same ideas that we worked with in the 2-variable system, but the process is a little bit lengthier. So let's just kind of run through some examples. So here's my 3-variable system. We'll do this with substitution first, and then we'll do an elimination example after that. Sound okay? So the only difference that's happening when we do these 3-variable problems is instead of having to do 1 substitution like we do in a 2-variable, we're going to have to do 2 substitutions, which is fine. It's not the end of the world. Okay. So the first thing I'm going to do is I'm going to look at the 3 equations and pick out an equation and a variable that's going to be easy to isolate.
Why?
Yeah, that's what I would choose as well. Again, if I have the opportunity to avoid having any fractions here, I would take that opportunity because it just makes life a little bit easier. So to get that y by itself, first thing I'll do is I'll subtract 6x and 4z from both sides, and then divide by the -1. And so what I'm going to do then is into both of the previous 2 equations, I'm going to substitute. So the other 2 equations that we haven't used, we're going to substitute into both of those. Everybody feel okay with what we're doing so far? So one of the things I see students struggle with consistently as, you know, as a math teacher in this kind of problem is just kind of staying organized. So if you're somebody that struggles with being neat and organized, this can be quite, you know, these kinds of problems can be quite challenging because there's a lot of symbols to, you know, to keep track of. You'll notice that I'm going to put it like a vertical bar, kind of dividing my two equations. So as I simplify these things, it's kind of easier to hang on to and figure out which equation is which or whatever. So now I'm just going to simplify things. So I'll distribute through my 2. And then combine my like terms. And then I'm going to move that constant over to the other side. And now that's as simplified as I can get. So I'll go to the other side and do the same thing. So I'll distribute through that -3. I'll combine my like terms. That's 7. And then I'll just add that -3 to the other side. Now what I've done here is these, as I've taken my 3-variable system and simplified it down to a 2-variable system. Everybody's okay there? And now this becomes just like a problem from last night. So if I wanted to solve this new system that I've written here in blue, would you prefer to use substitution or elimination in this case? I would use elimination also. Why? Yeah, it's already set up to go, right? Look at the x's. They're already opposite coefficients, so it's like raring to go to do elimination. It's begging you, please, please do elimination on me. So I would oblige and say, okay, I'd be happy to eliminate. So if this is equation A and B, we're just going to do A plus B because it's already set up to go. And I'm probably writing way more extra stuff than you would need. But, you know, they're notes. So you get what you pay for. So when I add the two equations together, I get 2z equals -12. And when I solve, then I get z is equal to -6. Once I have that, I can go back to any of the 2-variable equations and plug in my z. So for example, let's just say I plugged it into the first equation. And I can use that then to solve for x. Oh my goodness, guys. I said that 8z plus 3z is 9z. That should be 11, 11, 11, 11. So that's a 4. Jeepers creepers, Mr. Kulik. You could at least kind of check these things as we go so you don't make so many stupid mistakes. You know, I made a mistake. I'm sorry. Sheesh! Mr. K, that was a nightmare. Well, I'm sorry, guys. You know, I don't try to make mistakes, but it's 8 in the bloody morning, you know? It happens sometimes. Best laid plans of mice and men, I say. You know, at least mice. So far, so good. So now I can take both of these previous two and go back to any of these 3 variable systems or 3 variable equations and plug back in to get my y. And point in order, I'd probably pick this one that we used to do the substitution because the y is already solved for us, right? So y equals, I know that x is 2, and I know that z is -3. So I know that my y is 1. So I have 2, 1, -3 as my answer. Yeesh! Mr. Kulik, that was like a whole page on my paper. It's the way it goes sometimes. You know? See if we zoom out enough to get this on the screen all at once. Yep. So just to rehash what we did here from a high level. So we chose an equation and a variable to isolate. We used that isolated variable and substituted it into the other 2 equations in our 3 variable system. When I simplified, that gives me two variable equations, which formed a new system. I then solved that new 2 variable system using either substitution or elimination. In this case, I used elimination to get one of my 2 answers, or one of my answers. I then took that answer and plugged it back into a 2 variable equation to get a second answer. And then I took both of my 2 answers and plugged it back into any of the 3 variable equations to get the third. Does that kind of feel familiar? Again, we did this last year, so it shouldn't be like, I don't have any idea what to do. You know, it should be like, woof, okay, I kind of remember doing this, and it was just kind of a pain sometimes. Okay. So when we do elimination, again, kind of the same idea that we had before, except we're going to have to do more than one elimination. Everybody's okay with that? So first thing I want to do is pick a variable to eliminate. In this case, any choice would be a reasonable one, because when I look at my stuff, each equation has a variable with a coefficient of 1. So it doesn't really matter which one I want to choose to do, or which variable I want to choose to eliminate first. It'll be kind of equally, or it can be equally easy. Okay with that? So let's just say, for the sake of argument, we chose to use the x's. So what I'm going to do is I'm going to eliminate the x's from 2 pairs of these. So maybe I'm going to use A and C, and then I'm going to use B and C. Notice that the equation that I'm using in both of these eliminations is going to be equation C, because that's the equation where the x has a coefficient of 1, and it's really easy to do that. So what do I need to do, or what do I need to multiply the equations by for A and C to eliminate x? What's up? -3 to which equation? Just C, right? A can stay where that is, which is lovely. And then how about B and C? -6 times C. Everybody cool with that? Okay. So let's go ahead and write that out now and do our elimination. So -3 times C. So when I do that, I get -11y minus 11z equals -11. Woo! Look at that weird looking thing. All those 11s. There's my B. And then -6c. So when I do that, I have -26y minus 17z equals -44. Okay. So these 2 equations then are going to make a new 2-variable system. Notice when I do this, the 2 variables remaining are both the same in both equations. Right? Both equations have y's and z's in them. If that was not the case, you did something wrong. You eliminated 2 different variables in that first step. In one pair, you would have eliminated x's, and the other, you might have eliminated y's or something. Has to be the same variable in both pairs. Everybody's okay? Okay. So this equation then, or this system, again, we're going to do the same thing. We're going to choose a variable to eliminate, either x or y. I'm sorry, y or z. It doesn't really matter which one you choose. Doesn't look real appealing right now, though, right? Probably elimination would be the easier tack, but the numbers are going to get kind of big. Can I point something out to you that could be a helpful little time saver for us? You notice the equation where all the coefficients are negative 11? What if I just divided that whole equation by negative 11? That'd be a heck of a lot easier to use, right? Keeps the number smaller. That's fine to do. So I'm going to go ahead and take that little shortcut. I'll put a little note here that we just divide by negative 11. Can you always do that kind of a thing? No way, Jose, but this time we could. And boy, it's nice to see the stuff that like, hey, this comes up every once in a while. You're welcome to do that sort of thing if it makes your life easier. Do you need to do that? No. If I didn't do that, could I still done the problem? Yeah, it's no problem. All right, so let's say we're going to eliminate the y's. So what do I need to multiply the equations by in order to eliminate the y's? It's 26 times equation A, right? I don't even need to worry about it. Yep, B is fine just the way it is. So 26A, or 26 times A is that. And then B is fine just the way it is. Like all of you guys, you're fine just the way we are. And then when I do that, I add down, I get 9z, and then negative 18. So z is negative 2. And once we have this, we substitute it back into one of these two variable equations. It doesn't matter which one. I would pick equation A. That gives me y is negative 1. And then once I have this, oh, my pen stopped working. Does your pen ever do that in your OneNote? Just like all of a sudden it's just like, hey, yeah, I'm just done for right now. I find that sometimes it'll come back and sometimes it just takes too long. And if you just unscrew it, take the battery out for a second, like that seems to do the trick. So we have these two then. And then we can just go back to any of our three variable systems to solve for x. I'm going to plug those into equation C. Because the coefficient on x is 1 and it just makes the arithmetic a little, like a very little bit easier, but like I'll take it, you know. Oh, fiddlesticks, guys. Fiddlesticks. Z was negative 2. What did I plug in, though?
Positive.
Ah, Mr. Kulik, you did it to me again. I know, guys. I didn't mean to do it to you again.
So cool. I love these words. Never heard of fiddlesticks.
Well, if you were an older man, maybe we would have. Ugh. It's so frustrating.
At least you caught the mistake.
Yeah. Yeah. Okay. So now that I have everything, I have X, Y, Z as my answer. Sheesh. Do you know how to check these?
Yeah, so.
If you take your answer and plug it in, it should work in every one of them. And that's kind of a lot, but typically if you got something wrong, it's going to not work in the first one right away. Like just none of them, it won't work in any of them. It's very rare that you come up with an answer that works in one and not all the rest of them if you're trying to do this process. Oh yeah, okay. Yeah. So let's call this a day. Oh, we should do this. One more example. I lied. One more example.
Is this the last unit?
Yep.
So probably like a test next week then?
Yep.
Thursday?
Yeah, if you take a look at the board, I have all the rest of the relevant dates for this chapter up there, I think.
We're A.
You are A day. I think that's Thursday. Yeah, because today's only the 28th. Okay. One more example here. So let's say we have this system. What do you want to do? You want to do substitution or elimination? Again, it doesn't matter. You want to do substitution? Okay. Which variable, or which equation, which variable? Okay. So x is going to be negative y minus z plus 3. And we're going to just plug that in for the x's in the other two places. Okay, so let's go ahead and distribute the 4 through. Oh my crud. Anyway, I wrote down the wrong problem. This wasn't the problem I wanted to do. Anyways, so when I do that, I get 12 equals 7. So what should I say here? Solution. Do I care what happens in the other part? No. As soon as I find like a false statement like that, I'm done. Doesn't matter when it happens. If it's with the first elimination, second elimination, third elimination, whenever I find that, I'm done. All right, sorry. This is the actual problem that I wanted to do. I promise Mr. Kulik will stop being so dumb. Sometimes it just happens, you know. You didn't try to. Nobody's trying to be dumb. They just make mistakes. Jeepers creepers. Settle down, guys. All right. Substitution or elimination, which one do you want to do? I mean, to me, this is screaming elimination when I look at the A's,
Yeah, it's elimination.
right?
Okay.
I mean, A and B are already ready to go. I don't have to do anything to those ones. And then I can just do 2A plus C, and I'm good to go, right? Hopefully you guys see that. And Mr. Kulik prefers elimination. He just finds it tends to be a little bit neater. Or at least he thinks easier to kind of do in his head. Okay, so when I do that, I have 3b minus c is equal to 5. When I do this, I have 3b minus c is equal to 5. And at this point, do we even really need to say it? Yeah, it's just means infinitely many solutions right away, right? But we're going to actually ask you to do a little bit better than just that. So infinitely many solutions, we'd like you to be able to describe like how to generate those infinitely many solutions. In the two variable system, this is kind of trivial because if you have one, if they're both the same line, as long as you have the equation for a line, it's really easy to figure out how to get the points on that line, right? Here, though, it's maybe a little less obvious. So what we're going to do is we're just going to pick one of the two equations, now that we know that it's infinitely many, one of the two variable equations. And I'm going to isolate one of the two variables. It doesn't matter which one. In this case, I'm going to choose to isolate the c because it'll avoid any fractions. Everybody's okay with that? So I'm going to start writing my answer here. So in the C spot, I'm going to put 3b minus 5. Now, since there's a b variable in the b spot, I'm going to put the b. So far, so good. And then I'm going to take this and plug it back into any of the three variable systems that we had here. Specifically, which one do you think looks the most appetizing to get the a out of it? Yeah. And we said that C was 3b minus 5. So now I'm just going to get the a by itself. So I get a is equal to b minus 11. So there is my answer. So infinitely many solutions. And those infinitely many solutions can be generated here. For example, if I pick a value for b, say b is 0, that would mean that a would have to be a negative 11, B has to be 0, and C has to be -5, just by plugging in above, right? So that's an example of one of the infinitely many solutions. Or maybe I pick B to be 1. So I get -10, 1, and then -2. Or maybe I pick B to be 2, and I could do this forever, right? I could just keep picking values for B, and they'll keep generating solutions for me. So infinitely many solutions doesn't mean any ordered triple is a solution. It just means that there's infinitely many ordered triples I can find, but not every ordered triple, right? They have to kind of fall into this form. Does that kind of make sense of what we did there at the end? So when you get an infinitely many solution in 3 variable, I want you to find this. Now, just to be clear, there are 3 versions of this answer. We found the version where everything is in terms of B. There's a version where everything would be in terms of A, and everything in terms of C, right? So keep that in mind. If you're comparing answers with somebody, you may have a different answer than them, but it could still be valid. There's 3 different correct versions in terms of A, B, and C. Okay? Let's stop here.